Okay, so welcome to this problem solving session on DBMS. Today and the next class will be very important. If for why am I saying it? Because in case you plan to not study DBMS, uh, my suggestion will be never to leave a subject. Learn the most important topics at least. And the most important topics on DBMS is what is today's lecture and the next lecture, which is on normalization. Um, I believe you guys have been taught functional dependencies, right? No? Okay, that's strange. Okay, so that's fine. We will learn that today. Don't worry. It's not a very difficult topic. Just follow what I say, whatever I say, and if you are able to get it, okay. Please, then I think it will be easy for you to understand functional dependencies because it's an easy topic. Just there are some here and there tips and tricks that are required. So the idea of these lectures are to teach you problem solving and teach you concepts via problem solving. Okay, so let's look at an example. Okay, let's look at an example, and that way you will be able to understand what do I mean by functional dependencies. Okay, okay. See. uh, So FD is review. Um, okay. Let's draw. So now when we are in functional dependencies and in the next class we'll look at normalization, we are going into the territory of something called relational model. Now what is relational model? In a relational model, the data in a relational model, the data is arranged in rows and columns. Right? A few of the relational model concepts I kind of discussed in the last class, like columns are known as the attributes, rows are the different instances of the entity. So all that you should know. Um, so now we are in the territory of relational model. No more ER diagrams and all will be present in today's lecture and also the next lecture. So now when we are in the relational model, let's draw a very simple table. Okay, very simple table I will draw. Okay, it consists of an ID. Okay, it consists of a name. It consists of an age. Okay, and these are the three columns. Okay, very simple table I'm drawing. Let's say there is a person with ID 1, name is let's say A, age is let's say 24. Okay, there is a person with ID 2, name is B, age is let's say 26. Okay, let's say there is a person with ID 3, name is let's say C, and the age is let's say 27. There's a person with ID 4, name is A, and his age is also 24. Okay, is the table clear? The different attributes of the table: person has an ID, a name, and an age. Now, if I ask you a very basic question, okay, just look at these four instances of the table. Just look at these four instances. Can you tell me which column, if I just take a value of a column, I can uniquely identify the entire row? Understood the question? The question is, which column value should I take such that I will get a unique row for that value? It's the ID, right? So if I give you an ID of, let's say 1, you will tell me that, boss, ID of 1 means I get this row. There is no other row I get. I get the first row with the name of A and an age of 24. I will not get any other row, correct? Yes, is this clear? So far so good. Okay. So now this is called a key attribute. And why is it called a key attribute? It is an attribute using which you can get a row uniquely. Okay, so it's a key attribute. Chalo. Now this is done. Now let me change the question a little bit. The question is like this. See, if I give you a value of ID, okay, what are the columns that I will get from the database? I will get the name and I will get the age. Yes. Now, can you tell me if I take a column, let's say name, okay? If I take the unique uh, name, for example, if the name of a person is A, capital A, just look at the table, okay? There's no other row. If the name of the person is capital A, will I get a unique age or will I get two different ages? Will I get the same age or will I get two different ages? Just look at the table. If the name is capital A, will I get the same age or different age? I will get the different ID for sure, because name will give me, if a name is capital A, either the ID could be 1 or the ID could be 4. But if the name is capital A, I will get the same age. If the name is capital B, will I get a unique age or will I get different age? See, there is only one row with name as capital B, right? So definitely you will get a unique. If the name is capital C, will I get a unique age or a different age? See, there's only one row with name as capital C. I will get unique age. Similarly, if the name is capital A, even though there are two rows, the age you will get only one value, which is 24. So even name can uniquely identify an age. This is the most important concept of functional dependency. Okay, is it clear? Now, is this correct? Can name uniquely give me an ID? Can name uniquely give me an ID? Is this correct? If the name is capital A, will I get a unique ID? No. But let's assume, okay, just assume that the fourth row was not there. Then is this correct? Yes? Okay. Now, can I say that the name can give me the ID as well as the age? Can I say this? Assume the fourth row is not there, okay? Assume the fourth row is not there. Can I say this? That the name can give me a unique ID and an age. So, can I say that name is also a key attribute? Because name can uniquely identify each row of the table. Can I say this? I can, right? So, what does it mean? What do we learn from here? We learn that a table can have more than one key attribute, first of all. Okay. If you know this, now what I will do is I will not teach you concepts. Okay. We'll go to questions. I'll teach you the concept and then we'll solve the questions. Okay. That way it will be better, faster, and you will also think that there are questions for which you are actually solving things rather than me just dictating theory. So this is the concept of functional dependency. So let me just come back to the original table. Now name cannot uniquely identify ID. Name is not a key attribute anymore. So now this thing, right? So now these two things that I wrote, ID gives name, age, name gives age. These are nothing but your functional dependencies. Okay. Okay. Can you also identify any other functional dependency apart from these two? Looking at the table. Can I say age uniquely gives me name? If I have a value of age, can I get a unique value of name? Look at the table and answer. If I have a unique value of age, can I get a unique value of name? If the value of age is 24, what name will I get? If the value of age is 26, what is the name I will get? If the value of age is 27, what is the name I will get? Is there any possibility that given a value of age, you will get more than one name? See, you are only answering questions, right? So I think you know already now. So what does it mean? Can I say age can uniquely identify name? Yes. So age can also uniquely identify name. Now you might be thinking that if name can uniquely identify age, why then age can also uniquely identify name? That could be always true, but no. Let's say this was 24. Now tell me, if the value of age is 24, what is the name I will get? That is, you're not getting unique name, so it's wrong then, right? So that's why it's not necessary that if name can derive age, age can also derive name. Okay, so far so good. This is very basic funda of functional dependencies. Okay. Yes. Okay. Okay. Now, given of all this that I just taught you today, just now, there is a question in GATE. Okay. Now let's try to answer the question of GATE. Okay. Yeah. There is a relation instance. They have given columns X, Y, Z. Um, different columns are there. Which of the following functional dependencies are satisfied by the instance? Now, when there is a two columns on the left hand side, for example, you can see option A as XY, YZ, XZ. It means unique pair of X comma Y. If you take XY derives Z, you're not just looking at a unique X, you are looking at a unique X comma Y, like unique pair of XY values. Try to answer. XY derives Z. Can this be a functional dependency given the relation schema? Relation instance, sorry. XY derives Z. See, each value of XY is unique, right? In the table. Can you see that? Look at the pair XY. Is there any pair which has two instances? No, right? Like there's 1, 4, 1, 5, 1, 6, and 3, 2. These are four different pairs. And if there are four different pairs, obviously they will give four unique values. So that is true. So XY derives Z and Z derives Y. Is that correct? Look carefully. If no, why? Who is the problem? What is the problem then? Perfect. If Z is equal to 2, you're not getting a unique Y, you are getting two different Ys, 4, 2. Very good, very good, very good. Okay, now try to answer. Second option, try to look at the second option. So for this, I know the culprit is Z equal to 2. What about option B? YZ derive X. Each pair YZ is unique, right? Is it unique? Yeah, it's unique. So if it's unique, definitely you don't even have to look into the value x. Y derives z. Even each value of y is unique, right? You can see that, right, in the table. Each value of y is unique. So what is the answer? B. Okay. But just to learn, why is C not correct? Who is the culprit? What is the problem with C? See, yz derives x is definitely correct, because if you're saying option B is correct, so in option C, you do not have to look at yz derives x. So there is some problem with x derives z. What is the problem? X equal to 1. If x is equal to 1, I am getting a different values of z. I'm getting 2, 3, not exactly one value. So this is the issue with x equal to 1. Okay. Why is D not correct? What is the problem with D? Y derives x looks okay because y is unique. But what is the problem with xz derives y then? 1, 3. Very good, very good, very good. So xz derives y is 1, 3. Okay. Did you, sorry, why did I do tick here? Sorry. Okay. Understood, right? Yes. Okay. Perfect, perfect. Okay. Now, this is one of the most important questions in the entire gate. Okay. And there are many people who try to teach you in different ways. I will not teach you, I will teach you in my way, which helped me a lot. Um, Actually, this method I kind of found myself because of practice. So I'll just teach you that method and it will really, really help you a lot. Okay. So first try to read the question. Relation has 8 attributes, A, B, C, D, E, F, G, H. And the fields of R contain only atomic values. This is just to fill the question. There's obviously, if it's a relational model, each field will have atomic values. You're not allowed to have multi-valued in an attribute. F is a set of functional dependencies that they have given, and F plus is exactly the set of functional dependencies that hold for R. What is F plus? We'll look into that. Don't worry. Okay, it's simple. How many candidate keys does the relation R have? Okay, see how to solve these questions. Okay, um, first of all, what is the meaning of a candidate key? A candidate key is a key which can uniquely identify a row in a table. Okay, if you look into so if you remember, ID was an attribute that can uniquely identify a row in a table. If you remember the example I was showing some time back, ID was a attribute that can uniquely identify a key in the table, and that's why ID becomes our candidate key. Now there is a concept of something called candidate key and super key. Okay, there is a concept called candidate key and super key. So a key definitely consists of some set of attributes. For example, in what I showed you as an example, ID is one of the candidate keys because it is a set of attributes, and you cannot get a smaller set of attribute than that. ID is just one attribute, right? So if I give you another example, let's take a table like this: X, Y, Z. Okay, there's a table like this, and let me write here 1, 1, 2, 3. A, B, C, C, and Z is 4, 5, 6, 7. Okay. Now, if I ask you, is X a key attribute? Is X a key attribute? Will a unique value of X give me a unique row in the table. If the value of X is 1, will I get a unique row in the table? No, right? You will get two rows. Can Y be a key? Can Z be a key? Can Z be a key? So there is no key, is it? If I take a combination of X comma Y, will that be a key? If I take a pair X, Y, will that be a key? Yes, that will be a key because it can uniquely identify a column in the any row in the table. So an XY becomes our candidate key. Now candidate key XY becomes our candidate key means, can I get a smaller key than XY? Smaller key meaning if I remove any of the attributes, let's say if I remove Y, I will get just X, and we just saw X is not a key attribute. If I remove X, I will get Y, and we just saw Y is not a key attribute. So can I get a smaller key than this in number of attributes? That's why it's called a candidate key. Suppose I have XY and I include Z with it. Does it become is it still a key attribute? Is it still a key attribute? Can you still uniquely identify a row in the table? See, with the value of XY only, you could uniquely identify a row in the table. Having Z along with it or any set of attributes along with it wouldn't make any difference. Okay, it will still be a key attribute. But is this a candidate key? Is this a candidate key? Meaning, can you get a smaller key than XYZ? Yes, we just saw that. If you remove Z, you get a smaller key. But is still our key attribute. So this is our candidate key. This is our super key. Okay. Is the difference clear between candidate key and super key? Yes. Okay. Well, let's come back to the question. Okay. Discussing about super key in a question that does not require to be discussed, super key. But still, I think the idea is clear now. Let's come back to the question that we have. The feed relation has 8 attributes and we want to find the number of candidate keys this relation has. Okay. So just follow the method I will tell you now and you will be okay. Write all the attributes in your paper. A, B, C, D, E, F, G, H. Okay. Now look at each of the functional dependencies. Let's look at the first one. CH derives G. CH gives me G, meaning unique value of CH gives me unique value of G. So what do I do is I put a line from C, H, and I have an incoming H to G, meaning CH gives me G. Okay, is it clear? First step. Next functional dependencies is A derives BC. So I will take A and I will have an incoming H to B. I will also have an incoming H to C. Is this correct? Is this okay? Next is B derives CFH. So from B, I can get C. I can C already has an incoming H, so you don't have to do anything. I have F, I have H. Then it's E derives A. So I will have E derives A. Okay, A has an incoming H. Now F derives EG. So F, I will have an incoming H to E. I will have an incoming H to G. Which attribute does not have any incoming H? What does it mean? It means you can never get a value of D using the functional dependencies that are given. You will never get a value of D. So your key should have D, should definitely be present. Your key should have D definitely be there, because you cannot get the value of D using any combination of values. For example, if you take a combination of CH, you will uniquely get G. If you take a value of A, you will get BC uniquely. If you get a value of B, you will get CFH uniquely. If you get the value of E, you will get A uniquely. If you get the value of F, you will get EG uniquely. Only capital D is one attribute for which you will never get a value from any other attribute. Okay, so D must be there in our key. Now, what do I mean by that? You will learn later, but just don't worry about it now. Now, this is D. Okay, they are telling me to find the set of candidate keys does the relation R have. Now, what we do is we call something called the closure of a functional dependency. Now, what do I mean by that is closure of an attribute. It means I have D. I will put a plus here. Plus meaning I wish to calculate the closure, which means what are the attributes I can get if I have a unique value of D. If I give you a unique value of D, what are the attributes that you can get? One is I can get D itself. It sounds very obvious, but yeah, if I get a value of D, I will get D only. But as you can see, there is no other value I can get. Right? If you, for example, if I give you a value of CH, right? You can tell me, boss, I can get the value of G from CH, right? But from D, you can never get any other value except D. Okay. So far, so good. Any questions, concerns? No? Okay. Now D should be there in our set of candidate keys. Now what I will do is I will take each attribute starting from A to H and we'll append it. For example, first let's consider AD. Okay. Now we'll try to calculate the closure of AD. What do I mean by it is, given a unique value of A and a unique value of D, what are the set of attributes that you can get from it? You can definitely get A. I mean, it's obvious. And if you can get A, you can get what? You can get BC, right? You can get B, you can get C, you can get D because you're supplying the value of D, so you'll get uniquely D itself. What else can I get? Now that you have the value of B, capital B, can I get CFH? If I have the value of C, A gave me the value of B, C uniquely. Now B can give me the value of C, F, H uniquely. And 1 second. So now, if you have the value of F, you can get EG as well. So you can get E, you can get G as well. Did I get all the attributes of the table? So AD is one of the candidate keys. Understood, or should I repeat? I will take more example, don't worry. Understood? So now you will have to calculate for BD. So what is BD? I will definitely get B, I will definitely get D. These are just obvious, right? What else? Can B, if I have a unique value of B, what can I get? What are the attributes can I get? Look at the functional dependencies and answer. C, F, H. Good, good, very good. C, F, sorry, H. What else? Now you try to answer. What else? Look at the dependencies. If you have CH, you can get G, right? You can get G. So you get G. Okay. What else? See, I don't still have A, I don't still have E. Can I get A and E somehow? Can I get A? For A, I need to have E, right? Because E derives A. If I have E, then I will get A. Can I get E? How? Who is giving me E? From F. Very good. So I'll get E, and then E will give me A. Did I get all the attributes of the table? So this is also a candidate key. Okay. Now let's come to CD plus. See, you might think it's taking time, but it will not if you have practice. Okay. I can do this in 30 seconds. It's very easy. Okay. You just have to, it's very simple. So CD plus give me either C or D. What else? This is interesting. What else? Can I get anything else? So what does it mean? Is this a candidate key? No. Okay. This is not a candidate key. Okay. Let's go with DDs or something not possible. ED plus. Okay. So ED plus A, B, C, D, E, F, G, H. Okay. Now, what can I get? Can I get capital A? Yes, because I have E. If I have capital A, I can get capital B, I can get capital C. If I have capital B, I can get capital F, capital H. Can I get G as well now? Yes, because I have capital F. So even this is one of the candidate keys. So F, D plus B, C, D, E. So this is D, F, G, H. Okay. So D gives me nothing. So F gives me EG. So F gives me EG. E gives me A gives me BC, B gives me CFH. It gave me everything. So even this is a candidate key. GD plus. Will GD plus give me anything? See, D cannot derive anything. You can see there is no. Can G also derive anything? No. Even G does not have any outgoing edge, right? G does not give me anything. So GD plus is also gone. Last is HD plus. Does HD plus give me anything? No. HD plus is HD. Okay. So how many candidate keys we get? How many candidate keys we got? 4. Now, technically, what I should do, okay? And I'm not telling that it is required, but I will tell you why you should not do, okay? Okay, sorry. So CD was not a candidate key, right? CD was, you said was not a candidate key, okay? So what are the possibilities then? I have to increase the attributes by 1, which means I have to consider now um, ACD, I have to consider BCD, I have to consider ECD, I have to consider FCD, I have to consider GCD, I have to consider HCD. Okay, but many of them I will not consider. Why? Because I will not consider ACD, right? Because I got a candidate key with AD. If I got a candidate key with AD, if I consider ACD, will that be a candidate key? Will that be a candidate key? How? So if my AD is a candidate key, what is a candidate key? Candidate key is a key with the minimal set of attributes. If I increase it to ACD, will this be a candidate key? Will ACD be a candidate key now? Candidate key is a key with a minimal set of attributes. If you declare AD is a candidate key, ACD is not a candidate key, it becomes a super key. Okay, please remember these two concepts, don't be confused. If AD is a candidate key, ACD cannot be a candidate key, becomes a super key. Is it clear? Similarly, if you claim BD is a candidate key, can BCD be a candidate key? No, because you can remove the attribute C and still get a candidate key. So even this becomes a super key. ECD. ECD, is it a super key? See, ED is one of the candidate keys. So ECD has more attributes, right? Even after ED, you get ECD. So even ECD, I will not consider. Okay, FCD. FCD, is FD a candidate key? Yes. Will I consider FCD? No. Right? GCD. Is GD a candidate key? No. So I will have to consider that as well. Because if you say GD is not a candidate key, GCD could be a candidate key. Now, but if you look at the table, you will never be able to get table as in the set of functional dependencies. You will never be able to get anything from GCD. Will you be able to get anything else from GCD apart from GC and D? If you look at the functional dependencies, no, right? You will never get anything else. So that is gone. Last is HCD. HD is not a candidate key. If you have HCD, at max you can get G. You cannot get anything else than G, right? Because if you have HCDG, you cannot get anything else, right? So that's why even this is not a candidate key, even this is not a candidate key. Okay, so you can stop at this point, because if you increase it further, you will find that there will be a candidate key as a minimal set of attributes. Okay, you can stop here and say that, boss, there are only 4 attributes, and 4 is the right answer. Let me tell you, okay, 4 is the right answer. But don't just stop here. Okay, uh, by taking 2 attributes. If you do not get with 2, try with 3. If you cannot get 3, try with 4. If you cannot get 4, try with 5, and so on. Okay, but if you do practice more, right, please practice more in your free time, you will kind of get the habit that you'll only have to check for 2 or 3 times max. Okay, gate is also they know that you have 120 minutes only for the exam, 120 or 130, 130 minutes for the exam, 180 minutes for the exam. So they kind of also don't try to They try to make sure that you are able to do things by them. Okay. Is it clear? Are you able to understand this question? This is a very important question for your gate. Okay. How to find the candidate key. Okay. Now, if you know this, then there is a derivative question that is also given. Acha, theek hai, chalo, answer this. This one is also something very basic. So, from the relation instance of schema given that, we can conclude that what? A can functionally determine B, which means A can derive B. Okay, functionally determine is just a big word. It means A can derive B or A can determine B. Okay. Can A determine B? Functionally determine meaning if I have a unique value of A, will I get a unique value of B? If I have a unique value of B, can I get a unique value of C? Who is the culprit? What is the issue then? Who is the problem with B? B equal to 1. If I have B equal to 1, I am getting two values of capital C, which is 1, 0. That's why it's a culprit. So B does not functionally determine C. So which is the right answer? B. B is a stronger answer because A functionally determines B, right? And B does not functionally determine C. It's a stronger answer, even though C you might answer because B does not functionally determine C, but option B is stronger because A can functionally determine B, right? So option B is the right answer. No problem. Don't say sorry. No problem. Okay. We are all here to learn. So B, A functionally determines B, and B does not functionally determine C. Perfect. Perfect. Okay. Good. Good. We understood the basic then. Yeah. So they are asking what are the candidate keys of R. So one way is, as I said, just draw the set of attributes and try to find the candidate key. Other option you could have is calculate the closure of all the options, which means calculate the closure of AE. Calculate the closure of DE. Calculate the closure of DE. Calculate the closure of AEH, and so on. Just calculate the closure and then see which one gives you all the attributes. That will become our candidate key. Please try this out. Is AE a candidate key? Okay. Well, I could do it mentally. B, gives me C, I get A, B. Okay. I did it mentally and I think the answer is AE is a candidate key. Jigya, what are you doing? Solving or waiting for my answer? It's not. Which attribute you are not getting by doing AE? H. Right. Very good. Very good. Yeah. Very good. You won't get H. So what should I do? So does it mean that H should definitely be in the set of candidate keys? I mean, see, if you from the functional dependencies given, there is no way I can get H because there is no H on the right hand side, there is no H on the left hand side. So you need to have H initially in your set of values. So option A and option B are gone down the drain. They are not candidate keys, right? Because none of them have H. Okay. So is A, E, H a candidate key? Is A, E, H a candidate key then? Very good. Yes, it is. So A, E, H is, I can get A, get A, that's just obvious. Gives me B as well because I have C, D, we'll look at it later. I definitely get E because I have E. Now E gives me C, BC gives me D, and H is obviously there. Right? So A, E, H is one of the candidate keys. Okay. B, E, H, is it a candidate? B, E, H. Think so. Think so it is. Try to find out as well. B, E, H. B, E, H, B, C. BC gives me D, so B, C, D, E I got, H I got, and D gives me H. So is it a candidate key? It is, right? So B, E, H is B, E, H plus B, E, H, right? E gives me C, so BC will give me D, and D gives me A. So it's a candidate key. Okay, you need to be fast like this. That's the expectation. Okay, D, E, H. Yes. So how would I solve this? Is if I write D, E, H plus, so D, E, H definitely gives me D, H. D gives me A, and E gives me C. How will I get B? A gives me B. Then that's the speed you should have. Okay. You look at the attributes which are not there in your list of attributes because you need to have all the attributes that are there. Okay. And GATE 2005 had no MSQ. So if you get this as answer, that means option D is the right answer. Please do not look at option B, option C, sorry, BCH. Okay. Maybe it is, maybe it is not. You can look into that later. I think even that is a candidate key. I think I could be wrong. BC can give me D. D can give me A. I can never get E, right? BCH will never give me E, right? That is the problem. So BCH cannot be a candidate key. Okay, can I proceed? Is it clear? Okay. This is easy. This I don't know. I think they were exhausted with number of questions and they couldn't find the questions that they could ask. So they don't ask candidate keys. They're asking you what is the closure. Okay, plus and star. Sometimes they write it as star. Don't worry. Can you try to solve this? Which one of following is false? Okay, not true. So watch out for the words. Yeah, what is the answer, guys? It should not take so much time. Let me be honest. Is option A correct? There is no. You are getting all the attributes. CF plus. Option B as well. Option B gives me BG. G gives me A. So ABG. AB gives me CD. I get A, B, C, D, G. I can't get E because I need F for that. I can get E because I need F for that. I can't get F because I need E for that. Okay. Option B also looks correct because you need EF, right, to prove the point wrong. You can get A, B, C, D, G. You can check that, right? BG plus. So BG, from G you can get A. So you once you have AB, you can get CD. So you get A, B, C, D, G. Right? Okay. C is a problem. Is it? See, D is not a problem. I checked that now only. So C is the problem then. Okay. So let's look at C then. So I intend to calculate for AF plus um, A. Okay. So it's claiming that I can get C from somewhere. Can I get C from AF? See, F can give me, so this is B, this is C, this is D, this is E, this is F, this is for G. F can give me E. चलो ठीक है. Okay. AF can give me D. Okay. Okay. What else? DE can give me F. That is not something I'm looking forward to. F can give me E. I need C to prove the point that it is wrong. For getting C, I need to get B because if I need C, I need B. If I have B, I can say I can got C. But if I get B, the option will be wrong because the option does not contain B. See, this is how I am thinking if I am in the exam. Okay, the thing is how I should think before I answer, right? So that's the whole idea of these sessions as well. So for C, you need B. If you get B, then this option is wrong because there is no B here and there is C here. So that is kind of not possible. So you can say that option C is the right answer because you cannot get the set of attributes using AF. Okay. Any other option I should do for you if you are confused? Why are they correct? Or should I proceed? Proceed. Okay. 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 Vishnu, all good? Can I proceed? Okay. Thanks. So we'll go to the next question. What is the next question? Let's see. This is also another important set of questions that are there. And what you have to do first is try to find out. First, tell me what are the candidate keys in the relation. You guys should know now how to find the candidate keys. The first step is, can you tell me what are the candidate keys in this relation? You can follow my method. You can. Yeah, you can follow my method also if you want. My method has only one issue. If you have an incoming edge across all the attributes, then it kind of becomes difficult. You have to then do manual things. So just that much. AB only, no other candidate key. Okay. AC is not a candidate key. AD is also not a candidate key. AE is also not a candidate key. BC is not a candidate key as well because I cannot get A. A should definitely be there, right? Because you're not able to get A from anything else. A should definitely be there. AB is a candidate key, as you guys are saying. AC is not. AD is not. AE is not. Okay, perfect. Very good try, Vishnu. The answer is not three, but very good try. I know what you are doing. I absolutely know what you are doing, but it's a very good try. So um, it's a very good try. Okay. So see, AB is a candidate key. You guys are saying, and can I say ABC is a super key? Can I say ABD is a super key? I can also say ABE is a super key, right? So the answer should be three. It turns out it is not. Why? Can I say ABCD is a super key? Hold on. Can I say ABCD is a super key? And also every candidate key is a super key. Please know that, okay? Every candidate key is also a super key. ABCD is one of the super keys, right? Jigya, you're with me here? Any superset of a candidate key is a super key. So ABCD is a super key. Can I say A, B, C, E is also a super key? Yes. Can I also say A, B, C, D, E is a super key? Okay. Can I say A, B is a super key? Because every candidate key also is a super key. Can I also say that A, B, D, E is a super key? Okay, perfect. Perfect. So how many super keys have I got? But 8 is the answer. Okay, 8 is the answer. If you got it, good. But you will see, do I have to enumerate all of this? No, it's a combinatorics problem. See, I have AB, right? I have AB, and any super key can either contain C or not contain C, either contain C or not contain C. It can either contain D or not contain D. It can either contain E or not contain E. Right? Every super key can be either of them. So there are two choices here. There are two choices here. There are two choices here. Which rule will you apply? Product rule or sum rule? Product rule. What is the answer you get? 2 to the power 3, which is 8. So it's a combinatorics problem. So along with AB, you can either choose to put C or not put C. That's two choices. Multiplied by, you can either choose to put D or not D. Two more choices. You can choose to put E or not put E. You got two more choices. In total, you have 8 choices. So there are 8 choices. Okay, is it clear now? It's a very important question for your exam. And what if there are more than one candidate key? So you will have to calculate for each individual candidate key, just like how I did, and then add them. Apply the sum rule. It's a combinatorics problem. Okay, you need to do it for individual candidate keys, find the super keys, and then you add them. Okay. Okay. This done. Let's go to the next question. Next question is this. Now, this is something I have not taught you as yet. So let's do that now. Okay. The trick to solve this question now, they are not telling you to calculate the closure of an attribute. They're trying to tell you find the closure of the functional dependency. Okay. They are two different things. Okay. I will not write the comma. Okay. Don't just writing comma. It will take a lot of time. I'm just writing things as it is. So I have PR derives ST. I can write them like this. I can say PR derives S. I can say PR derives T. Why I do that, I will tell later. But they both mean the same thing. Do you guys agree with me on this statement? If I write PR derives ST, can I write PR derives S and PR derives T separately? I can, right? I mean, they mean the same thing. Okay. If if I have a unique value of PR, if they give me S T, I can also say unique value of PR gives me S, unique value of PR gives me T, but I cannot break PR into two separate entities. Okay, that's a whole concept that we already learned because it means a unique value of P comma R, unique value of P comma R can give me capital S, can give me capital T. Okay. Uh, so my echo dot is also speech learning functional dependencies, I guess. He's saying I don't know functional dependencies. Anyways, okay. So PR derives ST means PR gives me S, PR gives me T. Now the second one is PSU gives me Q, PSU gives me R. Okay, with me now? I just wrote them separately. Why I wrote, I will tell later. That's not the entire thing. But with me, right, till now? Okay. Right. So now, this means there's something called a trivial functional dependency. Okay. So what it means is, this is not a very good question to actually explain F plus. Okay. I'll maybe explain that separately in the next slide. So if you calculate F plus for this, right, you will get all of these four functional dependencies. They will all be present as it is. Along with that, you may get some other functional dependencies as well. Okay. PR derives RT. Can I get this? Is this possible given functional dependencies? See, from PR, I can get R because R is a unique, R is, if you're supplying the value of R, you can get the value of R. That is kind of understood. Along with that, you can get T. Why? Because there is a functional dependency, PR derives T. Okay, with me till now? With me till now? Okay. Now, PSU derives Q also you can get because that is one part of the original set of functional dependencies. You can see, right? PSU derives Q. They are saying PS derives S. Can I get this? Isn't it very obvious? If you give the value of S, you get the value of S. Isn't it very obvious? Right? So, the meaning of a trivial, so the answer is C, okay, in case you are wondering, but why? So, trivial functional dependency means if you have a functional dependency where your RHS is a subset of LHS, it is called a trivial functional dependency. Okay, is it clear? If your RHS of a functional dependency is a subset of the LHS, the RHS is S, the LHS is PS. S is a subset of PS. It is called a trivial functional dependency. Okay, is trivial functional dependency clear? Now you might think, why is this not the answer? PR derives RT. And see, it's very clear, it's basic, right? So LHS, RHS is not a subset of LHS. You can see that, right? Should I explain this or you can see that, right? The RHS, which is RT, is not a subset of LHS, which is PR. Do you guys see that as well? Because T is not present in the LHS, right? Even though R is there. Okay? So again, for people who follow gate overflow, there is a lot of talk on this question. Okay, you can actually go there and see. There is a lot of talk on this question, especially this question. Few people came and said, boss, there is something called semi-trivial functional dependency. Okay, let me be very honest. There is nothing called semi-trivial functional dependency. The concept does not exist. Okay, so that's why many people got confused between option B and C. Even they said C is the answer because that is stronger. Semi-trivial meaning there is some semi meaning R, because there is R which is common. That means there is semi-trivial functional dependency. I couldn't find any, shall I say? I mean, if I ask this question in an interview and someone answers me this, uh, sorry, I will actually not even reject. I might say something that he or she won't like. So that's kind of what because this concept is just very simple. A trivial functional dependency is a functional dependency which is RHS is a subset of LHS. Khatam, that's the old story. Semi and all, there's no concept like that. Okay. And even they have talked about it in gate overflow. It's not that I am deviating from that. They have also said the answer is C, but they have kind of talked about semi-trivial functional dependencies. The concept does not exist at all. There is some professor, I think, who maybe have taught it. And that's the whole point of having teachers who don't know their stuff, right? They don't even teach you the right thing. They teach you the wrong thing, and that is something that I get very annoyed with it. So please, if you go to a gate overflow, please don't be confused. There is nothing called semi-trivial functional dependency. Even the best person in gate overflow has cleared that concept out. So I think you can also look into that. So it's very simple. If the RHS is a subset of LHS, it's a trivial functional dependencies, or else it's not. Okay. So that's the whole point of this. Now, again, as I said, this closure is not maybe not very clear still. So let's kind of discuss about it. So closure means like this. See, let's take a set of functional dependencies like this. Okay, I have A derives BC. So A derives BC. C derives D. D derives E. Okay, let's take a very basic set of functional dependencies, and I want to calculate the closure of F. Okay, always my advice will be always break down the RHS. If the RHS has more than one attribute, break them down into simple kind of things. Okay, so A derives B, A derives C, okay. C derives D, D derives E. Okay, or maybe we can just part way with D derives. Let it be that. Okay, so with this, what I can do is see A derives C, C derives D. Can I claim that A derives D? If A can uniquely determine C, C can uniquely determine D, can I say A can uniquely determine D? Jigya? Yes. So that is also called a transitive functional dependency. So I can say A can derive D as well. Can A derive E now? A can derive C, C can derive D, D can derive E. So can A derive E? Yes. Okay. A can derive E. Okay. So A derives C. Okay. C derives D and D derives E. Can C derive E? And then D derives E. Is there any functional dependency that I missed? I think so, no, right? So this is the F plus, which is the closure of the functional dependencies F given by applying some rules. There are some rules that are there. Others are very trivial rules. The sorry, and there will be some people who kind of also add all of this. So A derives A, B derives B, C derives C, D derives D, E derives E. This is if you are giving a semester exam, you can fill your paper like this. It's very obvious. These are from trivial functional dependencies because RHS is a subset of LHS. And even people write AB derives AB, BC derives BC. If you try to write that, it will take a lot of time. So all that are trivial functional dependencies. It's just that F plus is a set of all the functional dependencies you can get given a set of functional dependencies F. That's it. Okay, it's a closure of the set of functional dependencies. Okay, let's now go ahead to the next question, which is asking. Okay, so you also need to know one thing. Okay, um, about prime attributes. So let's say there is a relation A, B, C, D, E. Okay, and let's say you found the candidate key as AC. Okay, okay. Now my A and C becomes the prime attributes. They are called the prime attributes because they are part of a candidate key. and the others, which is B, D, E, are the non-prime attributes. Okay, AC are the prime attributes, B, D are the non-prime attributes. Now I explained you, so I think you will be able to answer. So a prime attribute of a relation R is an attribute that appears there. Some or all. I think some is the right answer, because if you have AB also as a candidate key, right? If you even have AB as a candidate key, C is a prime attribute that appears in the candidate key AC, but not in AB. Right? And A is a candidate key that appears, the A is a prime attribute that appears in all the candidate keys. So typically you may have a attribute which appears in some candidate key of. Okay, so this is the concept about prime attribute. We will return to prime attributes when we talk about normalization. Yeah. How many super keys are there with E as key? E as key meaning E is your key. They have told that the capital E, they have not given any functional dependency, so you cannot calculate the candidate key. They're telling you E is the candidate key. Okay. How many super keys can be there? It's a combinatorial problem again. Either you can have F, you cannot have F. You can have G, you cannot have G. You can have H, you cannot have H. So how many can super keys are there? There are 8. There are 8. So, okay. Hmm. Now they have defined this gate 2024. Okay, so the functional dependency x derives y is termed as a useful functional dependency. They have come up with a new term, and they are also giving you the options. X is not a empty set, y is not an empty set, intersection of x and y is the empty set. If a relation has 4 attributes, how many total number of useful functional dependencies are there? Please try this out. I will help you do for one. Okay, I'll give you some hints. Okay, but you need to try this out because it involves a lot of thinking in terms of your combinatoric skills, your discrete maths. Okay, see, there can be 3 cases. Okay, case one is that there is one attribute on the left hand side. Okay, why did I write left hand side? I could write LHS. Okay, fine. Sorry. So there is one attribute on the left hand side. Okay, you have 4 attributes. You can choose one of the attributes on the left hand side. Understood what I'm saying? You have 4 attributes. You can choose one attribute on the left hand side. So how many possible number of ways do you have to choose one attribute? 4C1, right? 4C1 ways you can select an attribute on the left hand side. Okay, is it okay, everyone? Uh, so you can have, so let's say I selected, let's say there is a relation with four attributes A, B, C, D. I selected A. Okay. Can I have A on the right hand side? Can I have A on the right hand side? Can I have A on the right hand side? No. Why? What is the issue? Which condition am I violating if I have that? Intersection is not the empty set. Intersection of X and Y must be the empty set. Okay. Fine. So on the right hand side, I have three choices because I have four attributes. One attribute I've already selected. I have three choices. Either it can contain a B, it cannot contain a B. Either it can contain a C, cannot contain a C. Either it can contain a D, cannot contain a D. Okay, so either contain a B, not contain a B. Either contain a C, not contain a C. Either contain a D, not contain a D. Is it clear so far? So far, so good. Okay. So how many choices do I have? Please do not answer 8 blindly. There is one issue if you answer 8. There is one issue if you answer 8. Please think. If you answer 8, that means you are also taking the fact that it will not contain B, it will not contain C, it will not contain D. And if you select that option as well, you will be violating a condition. So you have to remove that possibility. Understood what I'm trying to say? I'm saying there are 8. You can say there are 8. Okay. But that is not the right answer because these 8 different types that you are saying, the B cannot, let's say the B is not there, the C is not there, the D is not there. Can this is this possible as part of the 8 options that you are saying? I am violating one condition. Which condition am I violating? Second condition. Y cannot be the empty set. So there will be 8 choices, but you have to remove this one choice where you have no attribute on the right hand side. Okay. So 4C1 times 2 to the power 3 minus 1. What is the answer of this? 28. 4 times 7, right? 28. Is this clear? Case 1? How about case 2? Case 2 could be that there is 2 attributes on the left hand side. So sorry, I'll write LHS, don't want to waste time. So on the left hand side, out of 4 attributes, you can choose 2 attributes in how many ways? 4, see 2 ways. Perfect, right? Now let's say I selected A, B. Which are the attributes I can select here? I can select C or D, right? Because I can't select A, I can't select B because they are part of the LHS. So I can choose to include C, I can choose to not include C, I can choose to include D, I can choose to not include D. How many choices are there? Please don't answer 4, as I said. How many choices are there? Think and answer 3, because I have to remove the fact that Y is empty. So 2 to the power 2 minus 1. What is the answer? 3 by 2, 6 into 3, 18. Right? 18 should be the answer. Okay. Another case could be, I'm erasing this so that I have some space. Okay. Another case could be that there are 3 attributes on the LHS. How many ways I can choose the left hand side? 4 choose 3, right? 4 choose 3. Good, good, very good. And if I have selected 3 items on the left hand side, 3 attributes, I have only one spot left because there are in total 4 attributes. That one spot, I can only select it. I cannot deselect it, because if I choose to, for example, what I'm saying is, if I have A, B, C, I can either select D or I can not select D. But if I don't select D, it will become empty, violating the second condition. So I have only one choice, which is to include it, right? So you can write it as 1. You can also maintain the consistency and say it is 2 to the power 1 minus 1, right? Just to maintain the consistency with previous formula, you can say this 2 to the power 1 minus 1 is also 1. Okay. This is what is 4 choose 3 into 2 to the power 1 minus 1, which is what is 4 choose 3 basically. It is 4, right? 4 choose 3 is 4. 4 choose 3 is 4 choose 1. 4 choose 1 is 4. 4 into 1 is 4, right? I don't want to teach you basic maths. So case 4, can there be a case 4? That is 4 attributes on LHS. Can there be a case 4? For example, if I have 4 attributes on the LHS, which is A, B, C, D, what should I put on the RHS? Can I put anything on the RHS? I cannot put empty set, because if I put empty set, I'm violating second condition. If I put any of the attribute, then I'm violating third condition, because intersection is not the empty set anymore. So case 4 is not possible. There are 0 possibilities. Now, case 1, there is 28. Case 2, there is 18. Case 3, there is 4. Which rule should I apply to find the answer? Product or sum? Sum rule. What do you get the answer? What is the answer? 50, right? 50 is the answer. Okay, good. Let's move to the next question. This is also concept, okay? This is an MSQ. Which of the following options is or are true? So the one way to solve this question would be, try to find the closure and see if you get, for example, let me give you an example. Option A is not correct. Okay? It's basic functional dependency thing, because option A says a unique value of x comma y will give you a unique value of z comma w. That does not mean that a unique value of x will give you z comma w, right? If you remember the start of the lecture, I gave you one example of a pair xy. If you need the pair to uniquely identify a column which is zw, it's not possible that you can get it only with x. So option A is not correct. Okay. Is option B correct? Yes, because if a unique value of xy gives me two values, z and w, then I can definitely get z also as well. You can break the RHS, you cannot break the LHS. Please keep this in mind. So a unique value of xy If it is giving me a unique value of Z and W, then I can certainly get a unique value of Z as well. Okay, so option D is correct. Okay, how about option C? To find out option C, no, wait. Try to find the closure of the XW and see if you get Z. If you get Z, that means you are able to get Z with X comma W. So it should mean that it implies XWZ. So please try to find the closure of X comma W. You can actually do this for all questions. Just try to find the closure of the RHS, whatever functional dependency is saying in the RHS, try to find the closure using the functional dependencies of LHS, and then you will see that you will get the answer. So what is the closure of X comma W? With X comma W, what do you get? Okay. So that means you are getting Z, right? Jigya? If you tell that from X comma W, I get the value of Z. That's why you put it in the set of attributes. So option C is also correct, that means, right? Okay. Option D. Option D is very simple. It's transitive dependency. That if X derives Y and Y derives Z, it implies X derives Z, right? It's transitive function dependency, right? So option D is also correct. So it's an MSQ, multiple select question. So B, C, D are the right answer. Okay, clear everyone? Please try this out. It's an MSQ again. The only way to do is just find the closure of each of the options. Find the LHS, closure of the LHS. For example, find the closure of PS, find the closure of R, find the closure of P, find the closure of PS, and see if you're getting the right hand side or not. If you get, that means that is one of the options correct. Please answer this correctly. I will not tell you anything this time. Please try to answer on your own. Okay, so the correct answer to this question is A, C, D. Okay, so PS plus, we get P, Q, R, S, T. It's actually a candidate key. You can say that. Right? P plus. So if P plus is the candidate key, then obviously PS won't be. So sorry. Let's see. P plus is P, Q, R. You won't get anything else, right? So PS is candidate key. So P derives R. You get P derives R. PS plus, you get PS plus I already had calculated. Sorry. PQ R S T. R plus will only give you R. It will not give you anything else. So P is something that you cannot get. So option A, C, D are the right answer. Okay, good, good. Now I don't know what happened. It was an error from my part that the same question is kind of repeated 2-3 times. So sorry, I'll just skip through them. Right. So okay. Now this is also one of the most important questions that I've asked in the gate. If you want to learn the theory of lossless and lossy decomposition, they are kind of more related towards information being lost if you try to. So, okay. So if you have learned normalization, the whole point of normalization is to kind of break the table down into separate tables so that there are three anomalies that are eliminated: insertion anomaly, deletion anomaly, updation anomaly. My suggestion will be please learn normalization before the next class. There are videos in this channel as well, the same room by your professor. So by your instructor who taught you. So please make sure you are able to know that. Watch those videos and come normalization because it's a whole new topic and it is very long topic. So the idea is you will decompose a relation into different relations such that insertion anomaly, updation anomaly, deletion anomaly are eliminated. Again, I myself have forgotten normalization to a very extent because I have lost touch with this subject since 4 years. Only concepts I know, that's why I'm able to teach now as well. So there are many some nitty-gritty things that are there. In functional dependency, this was one of the things that is kind of a bit more involved towards how you want to solve things out. So what we'll do is I will just teach you one method of how to find if a decomposition is lossless or lossy and dependency preserving. In that way, you can actually do follow this method for any question and you will be able to get the answer. It's an algorithm called the Chase algorithm. It's a very famous algorithm to find out if a decomposition is lossless or lossy. So let's do the algorithm and try to find what it means. So see, I will teach you the method of how things work here, and you will be. It's very simple. Okay, it's not very difficult. So first thing that you do is you write the attributes. We'll draw a table. Okay, we'll draw a table, rows and columns. In the columns will be all the attributes A, B, C, D. Okay, and in the rows will be, so see, what they have said is the original table contained 4 attributes. So this is R, which contained 4 attributes A, B, C, D. They have broken this table down into 4 different tables. Sorry, 3 different tables. They have broken this table down into 3 different tables. One contains A, B, another contains B, C, and another contains C, D. Okay, so they have broken this table down into 3 different tables: R1, R2, R3, and that you will write in the rows. So this is R1, this is R2, this is R3. Okay, so the setup of the table should be clear. The columns contain the attributes, the rows contain the relation. BD, oh sorry, don't know why I put BC. Sorry. So the columns contain the attributes, the rows contain the decomposed relations R1, R2, R3. Okay. Look at R1. R1 consists of the attributes A, B. So what I do is I mark A and B. Let's say I use a cross. You can use cross A, B, C, D, whatever. I use a cross. It's up to you, whatever you want to use. Okay. R2 gives me B, comma C. Okay. So I will mark B. I will mark C. Okay. And R3 gives me B, D. Okay. So far, so good. Is the setup clear? It's very simple. Just follow along. Okay. Follow along. Okay. Now please pay attention. Look at column B. Okay. If you look at R2, it says B gives me C. Is there a functional dependency B gives me C? There is, right? There is, you can see a functional dependency that B gives me C. So if I have a value of B that gives me C, I will have to mark the other places as well in R1 and R2 as well. Is this step clear? Or should I repeat? I did two things at one time, so sorry about that. But yeah, what I meant was there is a functional dependency. B derives C. If R2 has a value X in the column B and the same value is in column C, it should also be in R1 and R3. Is that what it means? What you have to do is, since B derives C is one of the functional dependencies, if there is more than one row having the value of B, then you will have to mark the corresponding value of C as well. Okay. Now C derives D. There are more than one row that contains C. So you will have to mark D. Okay. Is it clear? Yes. Okay. Perfect. Now, why am I not looking at A derives B? Because there is only one row with the value of A. Okay, there is only one row with the value of A. That's why I don't do that. And B derives C, I had looked into it. So B derives C. I have to mark all the rows with C. C derives D, I have to mark all the rows with C derives D. And D derives B, I don't have to do it because it's already marked. After doing all of this, is there a row which contains all the values marked, all the attributes marked? Is there a row that contains all the attributes marked? There is, right? There is a row that contains all the attributes marked. So if you find a row with all the attributes marked, it means it is a lossless decomposition. It is a lossless decomposition. Okay. If all the rows contain the values, if you find any relation R that contains all X's or all the fields marked, it means it's a lossless decomposition. So that kind of means that option C and D are not correct. First step is done. And with this, you can conclude that it is a lossless join or lossless decomposition. It means the same thing. There's no difference. So either option A or B is correct, depending on what is it dependency preserving or it is not dependency preserving. Now, how do I do that? That's even simpler. See, you had a set of functional dependencies. What it means is when you have broken this down into three different tables, the first table contains the attributes A, comma B. So is there any functional dependency that you see that can go there? I can see one, that is A derives B. Okay. If I have R2, which is the functional dependency I can move to R2? Look at the set and answer. R2 contains the attributes B, C. Which are the functional dependencies that only contain B and C? It's B derives C, right? You can see B derives C. So B derives C comes here. R3 has B, D, which is a functional dependency that comes to R3. Or is there any functional dependency that comes to R3? D derives B, right? D derives B can go to R3. Are you able to understand this point? Yes, Jigya, are you able to understand this point? Yes. Okay. What does it mean? It means that C derives D does not go into any of R1, R2, or R3. Correct? If I join these three dependencies, let's say I join it and what do I get? I get A derives B, I get B derives C, I get D derives B. Is it possible to get C derives D after joining? Is it possible to get C derives D after joining? Can you apply some transitivity or something you can do to get C derives D? No, right? I mean, can you get, try to see if you can? I don't think so you can get. I can get D derives C, but can I get C derives D? So what does it mean? It means after joining the three functional dependencies, there is no way I can get C comma D, C arrow D. So the original set of functional dependencies, and after decomposing and then joining them back, the set of functional dependencies, you are losing one functional dependency, that is C derives D. You are losing that. So it is not dependency preserving. Okay, is it clear? What do I mean by dependency preserving? It means you decompose the table into three tables. After you join them back, do you get the same set of functional dependencies that was given originally for R? You see, you are lost a functional dependency, which is C derives D, because of the way you decompose the table into three different tables. The best possible case of decomposing the table would be to have a lossless join. There is no information lost, and it is dependency preserving. Okay, that's the best case you will get. But in this case, the way it has been decomposed, after you join them back, you are not getting C derives D. That's why it is not dependency preserving. Option B will be the right answer. Okay. Any issues with this question? Can I proceed now? Ah, very good question Vishnu has asked. He is asking B derives D is possible or not. Is B derived D in the original set of dependencies, Vishnu? So you cannot add. Come on. You cannot add a functional dependency. It should be from the set of functional dependencies that are given originally. If originally B derives D was there, it would have been here as well. D derives B is there, so D derives B should be there. Okay. Okay. Are you thinking that D derives B is there, so B derives D should be there? If you don't think that, it's good. Then I have to teach you that concept as well. Many people get confused there. So okay, let's proceed to the B, C, C. No, so that's the whole point. So C is not in R3, right? C is not in R3, so you cannot do that. Okay. Oh, actually, you do have a point. Sorry. Actually, you do have a point. Very, very good, actually. Very good point. So, yeah, I kind of also missed it. So, what Vishnu is saying is very good thing. He said, see, the original set of functional dependencies have B derives C and C derives D. Can I say it has B derives D as well? Jigya, what do you think? So, B derives D should be there. So, very, very good point. Sorry, I actually missed it totally. I now remember, right? B derives D should be there. So here there will be B derives D as well. Okay. Now can you tell me you are getting C derives D? Yes. Are you getting C derives D? You can also get C derives B, right? You can also get C derives B because there is C derives D, D derives B. So you can get C derives B. Now tell me, is that C derives D? There is. So what does it mean? It means option A is correct. I didn't look at the answer to be honest. Maybe if I look into answer, option A will be correct. Very, very good point, Vishnu. Thank you. Thank you for actually helping me here. I was kind of also a bit um, uh, not surely blanked out, but kind of thinking like is very good point. Very good point, Vishnu. Okay, very, very good point. Okay, let's go ahead. That kind of means you understood as well. So, anyways, um, this is a big question, and we'll apply the chase algorithm to try to find out if this is what is the answer. Um, so there are two decomposition schemes they have given. This is the last question, so I might exceed the time by 5 to 10 minutes. So this is the last question. After that, there is no more questions in today's class. So consider the decomposition that is given here, and these are two decompositions D1, D2. You have to find whether which one is lossless or lossy. So let's do that. Okay. So the first step is always to write the attributes. So P, Q, S, T, X, Y, Z, W. And then you have decomposed D1 into R1, R2, R3, R4. Okay. For R1, you will mark P, Q, S, T. I'm doing this a bit quickly because I think you got it by now, how to set up the table. R2 is PTX, so PTX. This is QY, and then the last one is YZW. Okay, okay. Is the table clear? The first step. Okay. Now let's go over each of the functional dependency. PQ derives X. Are there two rows with PQ values marked? Are there two rows with PQ values marked? No, right? There is only one row, R1, which has PQ values marked. P derives Yx. Are there two rows with P value as marked? Yes. And now if you see, P derives yx means P derives y, P derives x. So you can break it down into two as well if you want. So P derives yx, which means if there is a row with P and x, there should definitely be a row with P and x. Y I will not mark because y as in attribute y I will not mark because there is no x here, neither there is an x here. We should make it consistent. Okay, so that's why I will mark. Q derives y. Are there two rows with value of q marked? Is there y marked in one of the rows? In R3, y is marked. You can see that, right? In R3, y is marked. So I will mark y for this as well. Okay. Are you guys able to understand this point, first of all? Yes. Okay. Y derives ZW. Are there more than one row with the same with y as marked? Yes, I mean there are R1, R3, R4, all have y as marked. Okay. Is ZW marked in any of the rows? Which row ZW is marked? For the rows which have y as marked R4. So you will also have to mark ZW. ZW. What does it mean now? Do you get a row with all values marked? Do you get a row with all values marked? So what is it? Is it a lossless or is it a lossy? Lossless. So D1 is a lossless decomposition. Very good. Now let's check for D2. D2 is P, U, S, E, X, Y, Z, W. And D2 has been broken down into four relations: R1, R2, R3, R4. Right? So R1 is PQS. So you'll mark PQS. R2 is TX. So you will apply TX. Okay. R3 is QY. So we'll put here X, here X. And this is YZW. So YZW. Okay. First step done. Now look at the first one. PQ derives X. Are there two rows with PQ values marked? Are there two rows with PQ values marked? No. So we'll not do anything. P derives Yx. Are there two rows with P value marked? No, again. Jigya, you are able to understand, right? I see only Vishnu answering. Yes. Okay. Q derives Y. Are there two rows with Q value marked? Is there any row which has Y value marked? For the two rows you are saying Q is marked R3. Okay. Vishnu, you got this as well? R1, R3 have Q values as marked. One of the rows, R3 has Y value as marked. So to maintain consistency, you have to mark this as well. Okay, good, good. Y derives ZW. Are there more than one row with Y value as marked? Is there any row for which Z or W or even ZW is marked? So I will also have to mark for the others as well. Okay. Now it seems it is lossy. To confirm, let's run over it again because we modified the table and did some more markings. We'll just verify it again. PQ derives X. We see no two rows with PQ value as marked, so we'll proceed. Yx, again we have to know P value as marked. Q derives Y. We do have our two rows with Q value I have marked, but they also have the Y value I have marked as well. So I don't need to do anything. Y derives ZW. Also, there is more than one row with Y value as marked. So ZW value I've also marked. Okay. Now there is no row in the entire table which has all values marked. It means it is a lossy decomposition. There is no row with all values marked. You can see, right? There is no row. So, which is the answer? What is the correct answer then to the question? Which option is correct? D1 is lossless, D2 is lossy. So, option A is correct. Is the chase algorithm clear? Just stop when you get a row full of X, full of marks. That means it's lossless. Done, story is complete. But if you don't get a full row full of X, please verify it again once, because you kind of modify the table, right? After modifying the table, try to verify the things, verify the rows. And if you still don't get, then you can mark it as lossy. And A is the right answer. I know the answer of this. A is the right answer. Okay. Okay. So this was all about today's lecture on Gyan on this. Any concept you want me to repeat? Did you understand the lecture, today's lecture, the basic funda of functional dependencies, how they work, how do you calculate candidate key, how to get super key, how to check for lossless, how to check for lossy, how to check for dependency preserving? All that you got, right? Everything is clear now? Yes? Okay. Okay. Next class is normalization. So it's a very important topic as well. Functional dependencies and normalization are the two topics that you must study before the gate. Please do not enter the hall without studying these two topics. I can kind of guarantee you that IIT will be miles ahead if you skip these two topics. So miles ahead, it won't be possible only. So please do not skip these two topics at all. Again, as an instructor, I will always want you to study all the topics, and everyone wants to study everything. So, but if you are planning to skip, if you think I do not have time, which definitely you don't have, because 2 months is also not there now. So please, I will suggest you do not enter the exam hall without functional dependency and normalization. It is my humble request. Forget gate if you don't know these two. Okay. I will be harsh, guys. I don't want to sugarcoat and say no, it will work. It will work. 2 months are there. I'm not that guy. Okay, I can't do that. I can't play with careers. But please make sure you know functional dependencies and normalization for your exam. Okay. You might see the slides. Answer to last question is correct. Can you confirm? Yeah, the answer is A. The D1 is lossless, D2 is lossless. Last as in before this or this one only? Oh, you're saying the dependency preserving one? That's a good point. I will just confirm. 1 minute. That's a very good point. I think the answer is it is dependency preserving. I'll just check this. I have the answers somewhere. Option A is correct, which is it is dependency preserving. Yeah, very good thing, Vishnu. Thank you again for you understood that means. So very good point. Please also correct me sometimes. I may make mistakes sometimes. Okay, I may. I'm also a person. But yeah, okay. Anyways, thank you for joining. If you don't have any questions, feel free to exit the call. We'll meet next week with normalization, starting with normalization. Thank you. Thank you for joining. See you in the next lecture.